All right, everybody. So this is our first post-lab video. The goal here is to help you take a look back on what you did during your lab to get a little bit better sense about what you were doing and why you were doing it. So first of all, let's sort of kind of situate ourselves on what the point of the lab is. Well, the lab is to get a sense about how a computer would calculate values of functions like sine, cosine. This exp means e to the something power, so like e to the fifth, or the natural log function, like finding natural log of 2, which is the focus of this lab. And this is going to draw on the use of Taylor polynomials and the radius of convergence, or the interval of convergence. So hopefully you read that background. This is explaining that one way to have values to find natural log of 2 is to have a list of values and you just go look it up. But that's really inefficient if we are going to take a lot of digits of accuracy. In fact, it would take like an unsustainable amount of storage. So instead, what we're going to do is we're going to use a Taylor polynomial. And the Taylor polynomial it takes a function that's not a polynomial function, like a natural log function, and it represents it as a polynomial function. In this case, the function that we're going to be using is the natural log of 1 plus x, and that is approximated by this Taylor series, x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. Let's take a look at this first exercise. What is this asking us to do? It's saying that, okay, we have this Taylor series, and we know that the difference between this Taylor series and so what we're trying to do in this lab is figure out how we can come up with a finite polynomial that approximate this natural log function reasonably well, because this is an infinite expression, and that would be impossible for a computer to calculate because it goes on to infinity. So we're saying, like, if we take the first 4 terms, would that be a good approximation? Or maybe we need to take the first 100 terms. So this first exercise is it's asking us to figure out if we take the first 5 terms, or if we take the first 200 terms, how good is that approximation on this interval right here from negative 0.9 to 0.9? And later on, we'll talk about why that interval is important. Another thing to pay attention to is that this first exercise is saying that if we can figure out this sum, n equals 6 to infinity of the absolute value of x to the nth power, that sum is an upper bound to the error that happens when we cut off a certain number of terms. Specifically, what this is saying is that if we take our true Taylor polynomial centered at 0, we will get x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus x to the fifth over 5 minus x to the sixth over 6 plus x to the seventh over 7, and on and on and on until infinity. So that's the actual Taylor polynomial. And we're saying, now what if we approximate the Taylor polynomial by only using the first 5 terms? So what if we used x minus x squared over 2 plus x cubed over 3 plus minus x to the fourth over 4 plus x to the fifth over 5 as our Taylor polynomial? So if we use this term, you can see that the terms that we are leaving out are all of these terms from x to the sixth and onwards. So in other words, a remainder is negative x to the sixth over 6 plus x to the seventh over 7 minus x to the eighth over 8, and so on and so on. Now, you might be thinking, okay, well, this remainder, if I wanted to express this in series notation, I've been doing the sum from n equals 6 to infinity of our sum, which is -1 to the n plus 1 times x to the n over n. We're starting it at 6 because that is the term that we're starting with in our remainder. Now, this sum should be the error, right? That's the amount that we're missing. But that's not the sum that we're using. Now, what's going on here? If we take a look back at the lab, what we're saying in this lab is that this sum that we have right here, we can talk about these absolute values in just a second, that this sum is less than some other series. So we're actually going to be using the direct comparison test. Let's parse out what's going on here a little bit. So what this is saying is that the error will be bounded by the remainder. So it's going to be bounded by the absolute value of that remainder, actually. Okay, so there's our error bounds. And then there's some other stuff in here. It says that the absolute value of the series is less than or equal of the series of the absolute values. What's going on there? So what we're trying to do is we're trying to say that this absolute value is less than or equal than the sum of the absolute values of what is inside of the series notation. And what this is saying is that if we took the absolute value of this whole remainder, that absolute value is less than or equal to the absolute value of each of the individual terms added together. We can kind of make that reasoning pretty easily. If we're mixing pluses and minuses in here, those numbers like act in opposite directions, right? So like if we have -2 plus 1 minus 3, we get a -4. If we just treated all of those going in the same direction, we treated them all as positive values, it would have to be bigger because they don't cancel each other out. So the absolute value of the entire series is smaller than the absolute value of the series if we take, or it's smaller than the series of the absolute values. So that's what this jump is. And that's what's going on right here in this line. So what that gives us then is that we have the absolute value of each individual term, and that is equivalent. We're going to go ahead and get rid of the negative. We don't worry about the negative. And we can also think about that n. That doesn't need an absolute value on it either because n is always positive. So this is really like the absolute value of x to the n over n. We can actually simplify that one step more. Since the absolute value of x to the n, that just means we need to take a power function and make it positive. Well, if the x value that's being raised to the power is positive, that's equivalent. So that's what's happening with this conversion that's going on right here to get to this term. Then what's being done is we're going to use the direct comparison test to bound this error term by a simpler power series. This is actually a geometric series right here, because this geometric series, we can actually find the sum of it using our geometric series sum rule. But this thing is a little bit harder to find the sum of. Why does that make sense? Well, if these terms are all being divided by n, where n is something that's 6 or bigger, well, it would definitely make the series larger if we dropped that n, because we're not dividing by a number. So what we've done now is our original error is actually going to be quite a bit smaller than this upper bound, but the upper bound is really friendly. And if we can find that this upper bound actually exists at a number, then we've bounded our error. So we don't actually need to know the exact error, we're just getting an upper bound for the error. So now what we're going to do is we're actually going to calculate this sum. So in order to calculate the sum, I need the only geometric series sum I know is that we need to start at 0. And then the sum is 1 over 1 minus r. So how can I get this 6 to be a 0? Let's think about what this means. This sum in here is like x, the absolute value of x to the 6th, plus the absolute value of x to the 7th, plus the absolute value of x to the 8th, and so on and so on and so on. I can imagine that I can actually, using the distributive property, I can take out an absolute value of x to the 6th, and what I'm left with is 1, or absolute value of x to the 0, plus absolute value of x to the 1, plus absolute value of x squared, on and on and on. And then this right here is my really clean geometric series. And I just have this multiplication factor on the outside. So if I look up here, back to this geometric series rule, what do I have here now? Well, I have the absolute value of x to the 6th times the sum from n equals 0 to infinity of the absolute value of x to the n. Okay, and then using the geometric series sum rule, I know that this is equivalent to the absolute value of x to the 6th times 1 over 1 minus whatever this r factor is. And that is the absolute value of x. And then if I multiply into the numerator there, I get the absolute value of x to the 6th over 1 minus the absolute value of x. And that was a hint that you were given during class. This right here, that is my upper bound on my error. Okay, so I'm going to use that expression to calculate my maximum error in the 5th degree case. So remember, we're going to go back to this window. I'm going from negative 0.9 to 0.9. I want to figure out what makes this error the biggest on that interval. And it's actually just going to be one of the endpoints. So in this case, you would have calculated your maximum difference by just plugging in 0.9 into that expression. So you would have done 0.9 raised to the 6th power over 1 minus 0.9. And let's go ahead and look at the MATLAB calculation of that. So if I get 0.9 raised to the 6th power divided by that term there, let's go ahead and run that section. I get that my error is 5.3. It's quite a big error. So a 5th degree polynomial is not a very good estimate of the actual value. And then if I was going to find the 200th, the maximum difference if we were using the 200th degree polynomial, I'm going to need to find the remainder from the 201st term onward. And if I do that, let's go back to MATLAB. We're going to change that exponent to 201, run that section again, and I can see that my error now is quite small. 6.3 times 10 to the negative 9th. So that's like 0.1, 2, 3, 4, 5, 6, 7, 8, 6, 3. So what this is telling me is that my 5th degree polynomial didn't do a very good job of estimating the function at 0.9, which would have been like the log of 1 plus 0.9. Okay, that's like finding the natural log of 1.9. The 5th degree polynomial didn't do a very good job. The 200th degree polynomial did a pretty good job. It got the error to be pretty small.
Okay, so we just figured out the difference in that remainder, those leftover terms for this 5th degree polynomial and the 200th degree polynomial. And that was on this specific interval from negative 0.9 to 0.9. But remember, the whole point of this lab was trying to figure out how can we calculate natural log of 2, which means that we want to actually consider this quantity here. So we want to plug in a 1 for x, which is sort of outside this interval. So we kind of want to see what happens. And in particular, we know that for this case that we talked about, if we have 200 terms, our error is something like less than 10 to the negative 8th. So let's say that we wanted to use the Taylor polynomial, plug in 1 to it, and try and get an error, that is less than or equal to 10 to that minus 8th there. Well, how long do we need to make the Taylor polynomial? How many terms do we have to use? So the whole point of this exercise was just trying to plug in values for n and seeing, how far can we go? So if we go back over to the lab, this MATLAB document, when we're talking about this natural log at 2, right? And we have this whole long series here. And right, so it was in this slot here that we could sort of change how long our Taylor polynomial was. So when we plug in 153, that means we're using 153 terms in the Taylor polynomial, which gives us an error of 0.696. But we wanted that to be less than or equal to 10 to the negative 8th. So we should probably make this bigger so the error is smaller, right? So I don't know, let's try something like 200, see how much it goes down by, right? So we run that section. And okay, so it barely changed. We're still at 0.69. Okay, so let's try something a lot bigger, right? Maybe let's go to 1,000. See what we get. Okay, so that's still not doing very much for us. Okay, let's just add on a couple zeros there. So sorry, this was actually this value here, and we were looking at the error down here, right? So, but we do see that the error was getting smaller. So we're getting closer. We're now at 10 to the negative 6th, 5 times that. So if we add on maybe a couple more zeros, okay, now we're at 10 to the negative 8th, but we still have this 5 out here. So we're still a little bigger, 5 times 10 to the 8th. We want to get under 10 to the negative 8th. So maybe one more. And okay, here we go. Now we finally got under it. So this is maybe a rough estimation. Maybe we could make this a little smaller. Maybe if instead of using this full amount, we sort of cut it down and did half of that. And we still see that we're under 10 to the negative 8th, and we're really getting close to that. So I'd say we're probably stuck around here. So something with 1, 2, 3, 4, 5, 6, 7 zeros, a 5 with 7 zeros. So that should be our answer for how many terms we need, approximately. 1, 2, 3, 4, 5, 6, 7. So that's a lot, right? We needed 200 terms when we were on this interval here, but then when we plugged in 1, we needed a whole lot more. So if we go on now to exercise 3, so we discover that plugging in 1 is kind of bad, but if we can plug in a value that's not 1, then our Taylor series acts a lot better, which sort of gives us this intuition that maybe we should try using this property of logs. We know that the natural log of 2, right, is the same as the natural log of 1/2 to the negative 1 power, right? And that's kind of a wacky way to write this, but what it lets us do is it lets us use our property of natural logs where we can pull out this negative 1 and multiply it on the outside, and then we're just left with the natural log of 1/2. Which remember, we want to plug into our function, and our function was natural log of 1 plus x. So here, we're going to have the natural log of 1 plus, okay, how do we get to 1/2? Well, we have to subtract 1/2. So we're going to be plugging in -1/2 into our function, and then multiplying it by -1, and hey, that'll give us the value of natural log of 2. So let's see what happens when we use this -1/2 value instead of plugging 1 right in, right? And so exercise 3 is doing just that. We're plugging this -1/2 in and trying to get under that limit of 10 to the -8. So we go back to the MATLAB and we say, okay, we're on natural log of 2, take 2. And we have sort of the same discussion. And again, here's where we can change our terms. We can plug in different terms and see what we get. So we see that immediately, if we start at the 53rd term, our error is about 10 to the -16th, right? So 53 is actually too many terms. So if we start with fewer terms, maybe we, I don't know, let's see what happens if we plug in 10. 10 terms good enough? Okay, not quite, but hey, that's still not bad. Maybe we'll bump it up to 20 terms. And okay, then we're getting right on that edge of the 10 to the -8th. So maybe we need to plug in one more term. That do it for us. Not quite. Maybe a second term. And okay, then we're under that threshold of 10 to the -8 now. So we only need 22 terms here. And we know it's exactly 22. If we did 21, that was too few. And 22 really gets us right there. So we can say that our exact answer for this exercise 3 is 22 terms of the Taylor polynomial when we plug in -1/2. Okay, so we've started to see that something's going wrong by plugging in 1, right? So what's special about this value 1 when we plug it into natural log of 1 plus x? Well, if we go back to this MATLAB document, we talked about what the Taylor polynomial looks like compared to the actual function. And so we have this really nice graph over here that tells us that right around x equals 1, this Taylor polynomial, the red line, is sort of peeling off from the graph of natural log of 1 plus x. So if we think about that, right, the Taylor polynomial isn't gonna match the function everywhere, right? So that's where we calculate this thing called an interval of convergence to tell us where does the Taylor polynomial actually converge to the function and where is it actually going to give us good values. So if we try and calculate the interval of convergence of the Taylor polynomial of natural log of 1 plus x, well, let's see what happens, right? So just as a reminder, our Taylor series was sum from n equals 1 to infinity of -1 to the n minus 1 over x to the n over n, right? And we want this to be convergent. So let's see, one good test would be the ratio test, right? So if we look at our terms, our a to the n plus 1th term is -1 to the n plus 1 minus 1, right? I'm just taking everywhere I see an n and I'm plugging n plus 1 in. X to the n plus 1 over n plus 1. And then my a to the n term, well, it's that same thing, just with n, so n minus 1, x to the n over n. And the ratio test says, hey, I should take the ratio of these terms. So I go ahead and do that, and I say the absolute value of a to the n plus 1 over a to the n is equal to, so I just kind of stick these two over each other. And then I draw a whole big line for this fraction, -1 to the n minus 1. Okay, so when I divide by this fraction, that's the same as multiplying by its reciprocal. So its reciprocal is n over -1 to the n minus 1, x to the n. Okay, and then I want to cancel all the terms I can cancel, right? So this x to the n will cancel all the powers except for that x to the x plus 1 power. So I can cancel these, and I'm just left with an x over here, right? Oh, and I had absolute values everywhere. Create those. And then this negative 1 to the n minus 1 is going to cancel everything but one of those minus 1s, but hey, it's in absolute values, so really I don't have to worry about any of that. So I'm really just left with the absolute value of n times x over n plus 1. Okay, so now in order to really finish out this ratio test, we say we take the limit as n goes to infinity of this ratio here. And we said that this ratio was n times x over n plus 1. Okay, so if we have an n to the first power over an n to the first power, those powers are equal, so they just converge to 1. So the only part that remains after we take this limit is the absolute value of x, and right, we already took the limit there. So we just sort of have this absolute value of x. And for this series to converge by the ratio test, we need that this limit of the ratios has to be less than 1, strictly less than 1. So we know that this Taylor series will converge when the absolute value of x is less than 1. So that means on this interval, the Taylor series converges from -1 to 1 with these open brackets. So when we plugged in 1, we saw that we had some issues, right? And 1 is right on the edge of this interval of convergence. It's sort of, on the left side of 1, it converges just fine. On the right side of 1, it won't converge at all. And that's exactly what we saw in the picture on this graph here, right? On the left side of 1, it's converging. On the right side of 1, it's not. It's going away. So we expect that it's probably really tough for this series to converge at 1 if it does at all. And we can actually check whether it converges at 1. We can go back up to our Taylor series and plug in 1 right here. And if we look, that'll give us a series like this Taylor series at 1 is the sum n equals 1 to infinity of -1 to the n minus 1, and it's 1 to the n over n. But 1 to the n is always just 1. So we end up with this nice alternating series. We can do the alternating series test on it to see if it converges. So if we take the absolute value of this term in here, we get 1 over n. And these 1 over n terms get smaller as you make n bigger. And so by the alternating series test, this alternating series does converge. So this Taylor polynomial actually works at 1, but since it's convergent from the alternating series, if you, so actually let's check whether it's convergent if it doesn't alternate. So if there is no -1 to the n minus 1 power up here, that would be like trying to look at the series n equals 1 to infinity of 1 over n. And we know that this series is definitely divergent. It doesn't converge. So this is a conditionally convergent series when you plug 1 in. So again, this is sort of just barely able to converge. It does converge, but it really doesn't want to. So that's maybe why we expect that in order to get some good error, we need 50, who knows, 100 million terms. Whereas when we plug in this -1/2, which is safely inside that interval of convergence, we only need a nice 22 terms.